Okay, we're going to take a look at another example where we're just going to build a type 1, type 2 error chart, and then we'll go ahead and we will go ahead and do the hypothesis test afterward. The University of Minnesota uses thousands of fluorescent light bulbs each year. The brand of bulb it currently uses has a mean life of 900 hours and a population standard deviation of 80 hours. A manufacturer claims that its new brand of bulbs, which cost the same as the brand the university currently uses, has a mean life of more than 900 hours. Write a type 1, type 2 error chart. Okay, so before we even conduct our test, let's build the chart to see what the errors are and what they would mean. So our population standard deviation, our population mean of 900 is going to be the basis of our null hypothesis, and the counterclaim more than 900 is going to be the basis of our alternative hypothesis. So those are going to become the two column headers under actual state. Okay, so the actual state, you're going to state what the null hypothesis is saying, which is mu is 900, meaning that the null hypothesis is actually true. And the other actual state is that mu could truly be more than 900 hours, which would mean that the null hypothesis is really false. Okay, so mu is 900, mu is greater than 900. Our decisions could be to reject the null hypothesis or fail to reject the null hypothesis, same as before. So we make the right decision if the null hypothesis is actually true and we don't reject that null hypothesis. That's a correct decision. We make the right decision if the null hypothesis is false and we reject the null hypothesis. That's the right decision. The type 1 error occurs when the null hypothesis is true and we incorrectly rejected it. A type 2 error occurs when the null hypothesis is false and we fail to reject it. And we're going to be asked to interpret the meaning of a type 1 and type 2 error. Okay, what is the meaning of a type 1 error in this problem? So you go here, you look at a type 1 error and you say, okay, here's the column header, here's the row header. Type 1 error means that the null hypothesis is true. The population mean light bulb life is really 900 hours. But we incorrectly rejected the null hypothesis. That would be the interpretation of a type 1 error. The population mean bulb life for the light bulbs is 900 hours, but the true null hypothesis was incorrectly rejected. Okay, I just changed the wording a little bit right here, but it really means the same thing. It means that we are incorrectly rejecting a null hypothesis that is actually a true statement. And now we're going to ask, what's the meaning of a type 2 error? So we're going to go back to our chart. A type 2 error occurs when the null hypothesis is truly false, but we fail to reject it. Okay, it's a false statement. Mu is truly greater than 900 hours, but we didn't reject the null hypothesis. Okay, so we would state that the population mean life for the light bulbs is really more than 900 hours, but we failed to reject the false null hypothesis. Okay, so the null hypothesis stated that the mean was 900 hours, but in reality, the mean is really more than 900 hours. We should have rejected that hypothesis, and we didn't. We failed to reject the null hypothesis. Okay, so that's the interpretation of a type 1, type 2 error for this problem. Note that you don't need to conduct the entire hypothesis test to interpret the meaning of a type 1 and type 2 error. Now we are going to go ahead and continue the entire hypothesis test. So in red, I have the important pieces of information. This is the same problem as before. The mean life is 900 hours, so mu is 900. Sigma, population standard deviation, is 80. And the Manufacturer has a new brand which is going to be greater, more than 900 hours. There's your counterclaim. Okay, now there's some more information. This is going to give us results about the experiment. The university has decided to purchase the new brand if, when tested, the test evidence supports the manufacturer's claim at the 5% significance level. So that's going to be our alpha, 5%. 64 bulbs, that's the size of the sample, n equals 64, are tested and the sample mean bulb life is 915. That's the value for X bar. And then the final question is, should the new bulbs be purchased? So we're going to conduct a hypothesis test, we're going to come to a conclusion, we're going to answer the question, should the new bulbs be purchased, and then we're going to analyze what type of error we could have made and what does it mean. The hypotheses. The population mean bulb life is 900 hours, mu equals 900, and the counterclaim, the manufacturer is stating that the population mean bulb life is more than 900 hours, mu is greater than 900 hours. So our null hypothesis states that the new bulbs are no better than the old bulbs. The new bulbs are just the same as the old bulbs. The population mean for the new bulbs is 900, just like the old light bulbs. The counterclaim is that the new bulbs are greater in life, bulb life, than the old bulbs. So mu is greater than 900. The mean of the sampling distribution and its correct symbol. This is a sampling distribution of sample means. So the mean of the sampling distribution is mu sub x bar. Remember, mu sub x bar is the mean of all the sample means. The center of the distribution, the mean of all the sample means, is the same as the mean of the population. So its value is 900. Its symbol is mu sub x bar. Normal or t distribution, my. It's based on the normal distribution for the same reason we have before. We've been given a population standard deviation and the sample size is greater than 30. The decision rule. So make a picture to help you come up with your decision rule. This is a test on the right hand side because we're testing that the bulb life is, or the counterclaim is that the bulb life is greater than 900. So in the center we label mu equals 900 in the center of our bell curve. And then because it's a test on the right, we put our alpha equal 5%, we shade the top 5% of area as opposed to the bottom 5%. So we shade the top 5% of area. We make a vertical line that borders that 5% of area. Now, eventually, we're going to look at our sample data. If our sample data produces a p-value that's smaller in area than 5%, that's going to give us sufficient evidence to reject the null hypothesis. If our p-value is anything greater than 5%, that's going to fail to reject the null hypothesis. So remember, a p-value is a piece of area. And that piece of area, we want it to be very, very small. So the piece of area is going to go from x bar all the way up to positive infinity. And if that x bar to positive infinity area is smaller than 5%, it means that x bar is further along on the right than if it were a greater p-value. So here's our decision rule. Reject the null hypothesis at alpha equal 5% if the p-value of the sample statistic is less than or equal to 0.05. It's the same decision rule. The only thing that changes is 0.05 versus 0.01. But every time we do a hypothesis test, it's going to be the same decision rule. You may have a different alpha, but that's the only thing that changes. Because you always want a small p-value. Let's look at if we look at the X bar that we got in this problem by looking at the sample data, the sample statistic is X bar, and the value of that X bar is 915. If we look at where that 915 lies on the horizontal axis, let's look at it right now. Okay, here's the mean at 900, here's the X bar at 915. The p-value that we're going to calculate on our calculator will be all of the area from this 915 all the way up to positive infinity. When the test is on the right-hand side, the p-value is calculated from X bar up to positive infinity. In the last example, on the left, the p-value was from negative infinity up to the X bar. So the way p-value is calculated is different based on whether the test is on the left or the right. Regardless, we still want a small p-value, because if we have a small p-value, it'll mean that X bar is pushed further and further away from 900, which gives you strong evidence to reject the null hypothesis. So the p-value of 915 will be the area to the right of 915, all this area up to positive infinity. So to find out what that p-value actually is, go to your calculator, go to the same z-test area, make sure stats is highlighted, and put your null hypothesis mu sub 0 900 in, then your population mean of 80, your population standard deviation of 80, your sample mean of 915, the size of your sample is 64, and your direction for this test is greater than. It's on the right, so you're using a greater than mu sub 0, because the test is that your alternative hypothesis, or your alternative hypothesis is stating that the mean is truly greater than 900. So your test is on the right. You calculate a p-value to be 0.0668. Okay, 0.0668. Now that 0.0668 needs to be compared to alpha. So if you consider that alpha is 5%, and then you look at 0.0668, which is more than 5%, that's 6.68%. Okay, what that means here, I'm going to use my mouse. Okay. If you were to take a look at where 0.0668 lies, where the vertical line for 0.0668 is on the horizontal axis, versus where the vertical line for the alpha is on the horizontal axis, the 0.0668 is going to be further to the left, which is closer to the population mean. Okay, means it's not sufficiently further enough away from the population mean for this to be a significant result. So the p-value in orange is larger than alpha. 915 is not significant. Okay, it's not sufficiently further away. It's not sufficiently different than 900 for us to reject the null hypothesis. So if the p-value were if the p-value were less than alpha, we would be able to reject the null hypothesis, but in this case, the p-value is greater than alpha, and whenever that happens, we're going to fail to reject the null hypothesis. So we're going to fail to reject the null hypothesis at alpha equal 5%. And we never say to accept the null hypothesis. This is like saying a person is innocent, and that's something that we never say in the judicial system. We just say not guilty. Answer the question. The question was, should the new bulbs be purchased? Well, if our new bulbs were significantly better than the old bulbs, then they would be purchased. But we haven't found them to be significantly better than the old bulbs. So no, they should not be purchased. We don't have substantial sample evidence that proves the new bulbs are significantly better than the old bulbs. Okay, since the new bulbs are not significantly better than the old bulbs, we're not going to purchase the new bulbs. So now going back to the same chart that we built before. What type of error is possible in this problem, in this hypothesis test? What type of error could we have made, and what does it mean? Well, since our decision was to fail to reject the null hypothesis, Okay, we failed to reject the null hypothesis. Here is our conclusion. So when we look at our decision and we fail to reject the null hypothesis, there are two things that could have happened. If the population mean truly is 900 hours, we've made the right decision. But there is a chance that the population mean is really greater than 900 hours, in which case we made the wrong decision. That is a type 2 error. That means that the new bulbs actually have a mean life that is more than 900 hours, and we didn't reject the 900 hours. We didn't reject the population mean of 900 hours. So that is failing to reject a false null hypothesis. Okay, so when you make the conclusion fail to reject HO, the type 2 error is what's possible, and what it means in the context of this problem is that the true population mean bulb life is really greater than 900 hours, but we incorrectly failed to reject a false null hypothesis. Okay, the null hypothesis stated that mu equals 900. It's false because mu is really greater than 900. But we failed to reject it. That's a type 2 error.